Okay guys, welcome to our Digitronix Nepal's second tutorial session on Xilinx ISE Design Suite, which will be targeting for Spartan 3 FPGA. Actually, most of our tutorials are based on Xilinx Vivado Design Suite, which is like a professional version of Design Suite from Xilinx. Actually, ISE becomes academic and ISE doesn't have any revisions currently, so it is almost at phase out stage. So we have Vivado Design Suite and different latest FPGAs tutorial on our YouTube channel. Keep subscribing our channel. So in this session we are going to talk about structural design and VHDL. So how to design a structural model in VHDL and how to create full adder from using or by using half adder. So we are going to create a half adder initially in VHDL. Then after we will create a full adder module. Then we will call component of half adder in full adder. Then we'll create a constant for full adder. Then we'll implement full adder in our FPGA source. So let's begin with our ISE Design Suite. So let's go to File, New Project, and create full adder struct. Sorry, initially we actually need half adder, so just write but project name is full adder. Sorry, we just need to write half adder module in next stage. So we are not going to change this menu. Actually this is target for Spartan 3. XC3S500 is our device name, and FC320 is our package minus 5 speed grade, so we don't need to change anything in here. Let's do next, let's do finish. And we need to have initially have half adder VHDL module. So let's have half adder. So we can also use VHD. And each half adder have two inputs. One is sum, one is carry. Isn't it? Both are. We can have half adder module here. So we are going to do very fast in this tutorial session because we already have talked about what are the each stages and processes in this design flow in previous first tutorial. So we are going to in a fast approach on this tutorial. So let's have a script of how half adder works. What is the architecture of half adder? Actually sum is combination of a, what is x over b, carry is combination of a and b. I think if this is not correct, you should correct yourself. So I just make a comment. So you can also this is comment section. So this doesn't signify anything. So just we have just created a half adder, so it is almost complete. A x or b, a and b. So we just need to add another source called full adder, because we are going to use two half adder and on OR gate in full adder. So we just need full adder. Next, and full adder also will have port A. So let's have different port: AF, BF, C in, sum. So we just named full adder port in differently because it will make us easy to understand which port is of which. So this is full adder module. So these are the ports of full adder. So for combining these two blocks, so for making you clear, here is our ultimate goal of full adder. Actually this green box is full adder, and there are two half adder in full adder. So in structural design, we need to call we need to initially make a half adder, and we need to call half adder module in full adder or top module. So we will need to have component section in full adder, which will call the ports of half adder into full adder, and then after we will have port mapping in full adder, which we will going to see soon. So we just have create a half header, so we can use that half header module, which is actually this half header. This half header is already created, so we can use this half header in two times. So one module can be used multiple times, so we are going to use two times of this module. So just a script, one line can call two times. So after that we will use also OR gate. So let's work on it. So we just need to we have already have created a half header, so we are working we already have worked on half header complete module, then we are working on this top module. So we need to have a component section. So actually component is like a function calling. So in C++ we use a function call, which is actually calling another function in this top function. So actually where is half header? So half header VHD. This name must be same as the age in here. So you can also copy this section. So we just going to use this, and we are going to change this into component. So component section is almost complete. And another thing we should notice about, because these two are connected, these two AABB of another full adder is connected. This is from another project. This is not relative to current project, but the architecture is similar to the current project. So we should care about like ABCS of half adder. So AB are connected with external ports of full adder, so they are directly connected. We will care about this idea in port mapping, while this SOM isn't has been directly connected to any external port. So this is given to another half header, which is inside that full header. So this section is actually be like a wire, because this is not a complete port and this is not anything. So we will declare this section as a W1, which is a signal like a wire, and we also need to declare this section also, because this is also not connected directly to external port, which is like these are external ports. So we don't need to declare any signal for like SOM, because this is connected directly to SOM of external ports. So we are going to use different signals. Signal W1, W2, W3. They are of STD logic. These are single bit STD logic. So we are going to do what is our methods or algorithm in this section. So in this section we need to do actually component port mapping. So FA1, let's have a label of FA1 of either VHD port map. So on port mapping, what we actually do is what the port of half header is going to map with external port, like half header A will going to map with AF, and B going to map with BF, and another port is SOM. SOM is actually, we have talked about, SOM is not given to any port, so we need to give some value of SOM into a signal. Signal is actually a W1. W1 we have signal, so let's have a carry into where carry is carry directly given to another thing, so carry is isn't also given to anything, so we need to have w to. Let's close this, and we are going to copy this section. Sorry. Okay, this will be fa2 header port map, and this a of header second header 2 will given to this w1, so this will be given to w1, this b will given to c in, so we just have part port c in, and this sum will given to sum. Actually we have sum, and another will be given to carry, not the carry, because we just need the carry is also given to w3, so we are going to give it to w3. We are almost at the end. Actually currently we have two modules, FPGA and full adder. If we write program correctly, then this will create a single module, because this full adder will going to insert two adder and OR gate in itself. So we will just see full adder in top module, and we can also expand this full adder. So these two modules need to be merged in single. So if we save this module, currently we doesn't have save, so it must be a single. So let's click on it. So it is becomes a single module. So there are two half header, because we have used half header 1 and half header 2. We have called this half header VHD 2 times, so this is 2 module. If we have called 5 times, then it will create 5 sections on full adder. So we have just remained something like we just need to have this OR gate. So we are going to use this carry and the carry, so into a port, which is actually a carry. We can also use a signal, but we are going to use carry less than equals to w2 or w3, isn't it? So we are almost at the end. So we have created a half adder initially, and then we have inserted this half adder into full adder, then we have make a port map, and then we have created a full adder which merges these two half adder, single half adder into oneself. So let's click on this, let's synthesize it. If we have some mistakes, it will give you some mistakes. So we have some mistakes, A or B, sorry, we have used D, so it need to be corrected right here also. Where is, so I think now it is corrected. It will synthesize these two modules at once. So we are just synthesizing this because it consists of two. So if we expand it and view RTL, then this will be the RTL which we required in. This is our RTL. This is actually from a different project, so we just need to close it. So you can take a screenshot of this. So here is A of full adder, B of full adder, C in carry, and sum. These are half adders as we required. So what we need to do is we need to let's go to full adder. We just need to have constant. Let's again add a new source. Let's have an implementation constant file. We are going to make a constant for full adder because our main module or top module is full adder. So you can do next, we can do next, and we can sorry, sometimes the module we have add might not appear it here. If that happens, we should have to have different methods, so we can add another times too. So it doesn't give us any idea. So let's move to another method. So let's if the added module doesn't appear yet here, then you should close this, and you should go to your local repo. Then you should even re-open it, then it might show you. Again we have same issue. So let's again go to here. If this doesn't appear, okay, I have used another method because we already have created a constant. So let's go to add source. There is constant, there is 2 UCF we have connected created initially. So let's click in full add constant. Let's click, you can go to here. Now we are going to follow this section because we just need to have 3 inputs. This user guide 230, so you should have this Spartan 3 user guide use 230. Then you can go to here. We have just copied this location of switch. You can also type yourself because we can type it. I mean very fast approach, so I'm just going to copy it. So I just need to use these ports, logical ports AF, BF, C, AF, BF, C, AF, BF, and C. So we also need to have 2 extra output ports. Actually we are going to use output is LED. So let's go to LEDs. Let's copy 2 LEDs. There is another approach also for constraining, so we can use another approach too, but we haven't introduced you yet about another method. So let's follow these steps. It is also easier steps, and there is another also steps. So let's save it. So let's implement it, and let's generate, and let's configure target device. Actually we are not going to configure this time also. We have certainty of this design will be easy to easy to configure or upload. So we are going to show you some simulation instead of constraint, instead of configuring the FPGA. So let's add a source, new source of VHDL test bench. Full.tv. Sorry, I need to check full adder. So this is also a combinational circuit, so we also don't need to have this section. We can even remove this section. We also can remove this section, and we just need to remember about the parameters AF, BF, C in. AF, BF, and C in. So what we need to do is provide A with 0, copy this section, section 2, Control C. Okay, this is the main first stage for full adder. So what we are going to do is copy this section and paste this section 3 times. 0 0 0 0 0 1 0 1 0 00001 So we need to have 2 to the power 3, that is 8 stages. So we are going to copy 001010101. Sorry, 100. And after 10101. Then after 1 110. Then after 111. Is there 9 stages? Sorry, 1 2 3 4 1 2 3 4 5 6 7 8. These are 8 stages. Now we are going to save it, and we should switch on simulation. This is our top module, this is our simulator. We will check it and we will run the simulation. It must give the output of carry and sum, so users need to click on some type of view. So let's click on here. This is A B C 0, A0 B0 C in 1. So what will be happen is sum will be sum will be from A, B and C, A plus B plus C, like A plus B plus C. Then it will also give carry 0 1 0, sum high, carry 0 0 1 1. What will happen? 1 1, sum of 1 1 is 0 and carry will 1 1 0 0 1 0. So 1 0 1 2 1. So 1 1 plus 0 1 1 plus 1 0, sum and carry is 1 1 1 0, same, carry is 1 and 1 1 1 1 plus 1 0 with carry, and 0 plus 1 1 with carry, 1 with carry. Okay, this is the simulation. If you implement it on your FPGA, it will also work, because we provide certainty of this design. So you should generate PT stream and you should configure yourself. Actually, we also need to show you some configuration steps as we talk about. Go to OK, but we don't have connected currently initialized chain. You should get 3 devices and click yes, then go to .bit file of this local address. So there is bit PT stream in full adder struct. Then click yes, open. Then you should click about bypass 2 times for PROM and CPLD. Then you should click apply. Okay, then you should come here with FPGA or first chip. Then you should click program. Then you should get about program succeeded. Then you should check on your hardware by checking inputs of these 3 switches. 0 0 0 0 0 1. If this is high, 0 1 0 0 1 1 1 0 0 1 1 1 sorry 1 0 1 1 1. 8 stages you can verify it. So this is the steps for verifying the design. So this is our second tutorial session on the ISE Design suite, how to create a structural design in VHDL and implement in Spartan 3. This structural design is applicable for any design tools, because it is from VHDL. So this is feature of VHDL. Structural design is feature of VHDL. So we are using same method of creating structural design in Vivado or any design tools like Kratos. So thank you guys for watching. So this is the second tutorial session. We will make another tutorial session in later.